I know.
All right, everyone. I will slowly, very slowly start. So no stress. Like prepare yourself for another 1 hour towards the time series. And I just wanted to mention a little bit about the technical complications, difficulties. So indeed, we have three environments where you can run things, right? One is the link that you can find on the github.com /LiCSBAS. And if you search in the tutorial, you can see that the latest tutorial is available here that you can directly run using Binder. So that's the link you can return to it. And then there is the collab version, and then there is the local Jupyter Hub. I can tell you that none of them is working 100% reliable. So we just noticed several things. So I fixed one, but we cannot do more. So Binder has negative aspect if you are using it. If you are using it until now, it probably the session probably expired, and you will need to run it again. So just run it again, and hopefully you will get there. If there was some, oh, it's building now. So that's again on me because I updated some little thing there. Sorry for that. So it will take a little bit more time after the 2 morning. If you use the Google Colab, well, I am not sure that everything will work there, but that's because of Google Colab using the latest matplotlib indeed, and there are the errors, but as a workaround, if you use Google Colab, see some error, you can ignore it because the plots were pre-generated, so you can anyway see them inside the tutorial. So you can still follow us in Google Colab, and it might be more stable. For example, now the binder takes ages for me to run only because I updated the now 2 minutes ago. So the third thing, the Jupyter Hub had indeed an issue with the path. The path was assuming you are in home folder, which you are not by default. So that's on me, and that's why I actually updated that Jupyter notebook. So if you were running on our Jupyter Hub, then you can just refresh your page and maybe rerun the first. You should always rerun the first cell. Yeah, you return to the environment. The first cell includes some checks and some imports. So if your kernel died, for example, it was written, then just rerun the first cell, and then you can scroll down to the time series path, and it should work for you fine. there is yet another thing that unfortunately, even in the local Jupyter Hub, the last part about visualization will not really work. And that's something strange with the installation of some libraries. So yeah, technical issues are always here. Um, yeah. So actually, Binder is the most stable option, but I'm not really sure if every one of us can really connect to it due to the limited number of nodes. If we're lucky enough, have the Binder running, that's great. If you will want to return to this session later because everything is recorded and so on, then feel free to use Binder. It will work that time because it will not be such demand in the same time from the people. Okay, I will assume that that you are fine, set and go. I had that thing that I had to restart Binder, so I rerun the first cell, and it sets things up, and so I can scroll down just to the steps 11 to 16 to continue during the following 54 minutes. Um, so I have to abandon the online participants, but I hope that my assistant will deal with any sort of technical issues. Again, like online participants, if you get to the troubles with you cannot get to Binder and you don't have Google account, just watch. Um, and um, and if there are any technical difficulties here in the room, just let me know. Are you all fine in Jupyter? Fine, great. So great to hear that.
And just to say that it's now the error is that permission is denied. Permission is denied. So don't worry, I'm just going to use the stable version. That's the older version.
Yeah. So okay, thank you for that notification. There was indeed some issue that's about the part that I mentioned. That's now fixed in the Jupyter notebook, so it doesn't matter really. It doesn't matter. You can use the stable version because we are going through the core functionality. So guys, if you open the local Jupyter hub, it doesn't matter now if you use LiCSBAS or LiCSBAS stable. I think that the LiCSBAS is updated indeed. There are some different pictures shown, but it will work. Yeah, and that's important. So yeah, if you were using the ordinary LiCSBAS, the latest, then note that indeed I had some issue with path and I fixed it just now. So just refreshing it, you will be able to continue there. But yeah, it really doesn't matter. Yeah, for now. But thanks for that. Yeah. Okay. So let's start with doing the time series. So we have all our uncapped data and GACOS data downloaded, GACOS applied, and just by this LiCSBAS 03, maybe we clipped the whole frame to smaller area around the volcano here. That was all about here, and it's pre-processed. So I will show you the pre-processed data. So if I run the cell 06, you can see that we are in this directory. Yeah, so that's the home directory, and the frame ID. That's the one that we are working with. And by ls, I'm checking what is the content. So there are three folders. Geoc, that's where we downloaded the data. ML2 means afterwards it was downsampled by the factor of 2, and GACOS was applied. Then it was crypt, so it's again generating the data, but this time crypt into the other directory. And actually, you might see also the pre-processed data. Some part of it was pre-processed here simply, and that starts on TS for time series. So that's the folder name convention. So yeah, so that's the content. So you can see that the data is already pre-processed here. So we want to actually start kind of not really from scratch, but when we we would not have this TS folder, right? So let's have a look first of all what we have in that folder, geocml2 Gacko script. So by running this cell, you can see that the folder itself contains almost 900 virograms. And here you can see listed the last 30 folder names. Each of the folder contains the unwrapped data and coherence. Plus, there are some other data that are downloaded, like baselines, and yeah, and you should see the Gakkos info, the one that I showed you before. It's automatically generated in that folder after the step 03. Okay, so that's for information. We can have a look at the interferogram network. That's the other cell, and okay, that will that part may end up in some, as I mentioned, the strange error in the Google Colab, but in the end, the display should work fine. So, okay, so here this cell would actually use the interferograms that are inside the folder, will put the list into the text file and run a command that will generate the interferometric network PNG files. And this is then for your information, like first 10 interferogram pairs, just to see that for each of the epoch we have 3 other epochs. So that's our connection. But okay, but seems the problem is already here. Okay, let me see. That's strange. Um, yeah, well, there's a network. Okay. Does it work for anyone? Does anyone see the network plot?
Yes.
So is it only on my side? No. Okay. Okay, that's interesting. So I cannot show you the network plot now because of the. I will show you later how does it look because there is some pre-generated. Apologies for this. There is some there was some change with matplotlib library, and for some reason we automatically get the latest, and I'm not sure what are the changes. So okay, we'll get into it. That will be solved very fast because we should not have that happen. Sorry for that. Yeah. So actually, maybe that can be good point for me to show that if you get some things that are bugs, uh, please inform it. Please inform it on the webpage. You can put issues. Honestly, there were a couple of issues that were waiting for too long because we were not really that well used to that issues, but we improve. So if you have some bug, you found it, please create a new issue so we can or check first of all if the issue doesn't exist so we can really get some proper feedback and that helps improving things, of course. So yeah, so this one is an issue. Anyway, let's just go on. I will show you the network plot later. So we can have a look into some of the random interferogram. So actually, what I'm doing here is I'm looking at the folder for each of that folder name. There is not only .unv for the data, but also we generate PNG previews, so you can see yourself the pictures themselves. Yeah, so this is just a random example for you to see that we clipped the whole frame that is yeah, large, hundreds of kilometers, to a small area that covers the Campi Flegrei caldera, which is somewhere close to center or basically whole area. And yeah, so you see some signal, right? Okay, it can be small deformation. This is this would capture any signal within that 12 days. So it can be some deformation within that 12 days, or it's probably atmosphere. Yeah.
Milan, can we share the screen? So I've only just been able to access the
Okay.
comments, but apparently the screen's not been shared.
I'm not shared.
Apparently not. Sorry, I've only just been able to access the
Okay.
Q&A.
Yeah. Well, thanks for letting me know. Yeah. Okay.
Is that okay
Yeah.
for everyone online?
Okay, apologies for this. I was too much focused on the technical issues, but only to get you back. So once you get to the binder around the first cell that sets things up, and then scroll down to the steps 1 1. 1 means like time series. Yeah, like model 1 is for time series. 0 is for pre-processing, and then I have just run the other things and I'm displaying only an example of data. But let's go further. So what can we do? What can we see here in that cell? That's something that I actually also already showed. So I will only briefly. That's just showing that not only the PNG of the unwrapped data, but if you use the GACOS, it would also generate the nice PNG files for each of the interferograms, so you can see visually how much the GACOS, which is the one on the right, the PSLD, corrected the original unwrapped data. Here is the unwrapped version, and that preview is generated before the clipping. Yeah, because we first apply GACOS correction and only then clip. So we don't regenerate the PNG. That takes a long time, and most people don't watch it. But you can find a lot of information also in that the GACOS info. But that's the same thing that I was showing in the presentation. So you just for you to know that inside the GeoML the GACOS script directory, there is the text file which gives you information on the reduction rate of the basically of the STD. So it says about improvement, but you can see sometimes it has positive positive value. So it seems that the things get sorry, opposite. Sometimes it has negative value, so it actually sometimes have negative reduction of the STD, which means actually increase of STD. So it can say that in some cases, GACOS corrections does things worse, but you are anyway checking about the average thing, and this is standard deviation. It can it basically say that after the correction it's less flat, let's say. So it's just for you to know that the GACOS is also limited as all the models are. So yeah, but still a good idea to use it, I think. Okay, so that was actually still about the pre-processing part. Sorry for that. So only now we are getting into the basic time series analysis. Okay, so as usual, we have the name convention, LiCSBAS, then step number, and the steps for the time series are starting on 1. The pre-processing was 0. First of all, we have something that helps us to check unwrap the data, and here you just see some examples how bad the data can be. If they look ugly to you, it's probably bad. Of course, you are focusing on some smaller area, so if that is consistent, you can just ignore how it looks anywhere else. But anyway, that's just to show you what can be, what do we search for in this first step. So that's optional as well. Searching for some really strong overall gradient to some error that can be corrected as well. And I'll show you the help for this function. So this is the like first sieve, right? You are sieving your data. So first of all, you want to identify what is really very bad. So here this unwrapper check is working on the whole image, whole interferogram. So it will check the threshold of average coherence. So it gets the average of the coherence of that whole image. And if it's almost zero, for example, by default 0.05, which probably means you would see just black or no data at all, basically, or something went terribly wrong, or you are in a fully vegetated area, which is weird, but can happen. So this is average for the whole scene. And therefore, you should be a little bit careful to not to drop things that actually can be useful, that have only some patches, let's say, they correlated. So don't be too strict here, I think. Or you can use -u, which is threshold for coverage of unwrapped data. So, for example, here you can see that maybe only 10% of the data is actually unwrapped, right? Everything else is masked, probably due to the low coherence. So those two variables are a little bit connected, but if you want to keep only data that are mostly covering it, then you just increase the threshold. We are not very strict here, actually, and the significant azimuthal ramp is optionally with -f. What can be useful sometimes is setting the minimum or maximum temporal baseline. So, for example, if you know that your area will decorrelate in longer term, right, and you want to avoid the interferograms that are too long. Sometimes we generate 1 year long interferogram. If there is unwrapping error and you don't properly catch it, then it will affect negatively uh, your inversion, right? So you can limit it this way. Same for minimum btm, because on the other side, if you have vegetation in 6 days, the vegetation doesn't really correlate, so you will see nice signal. It will be unwrapped everywhere, but what it unwraps is basically vegetation signal, right? Which will then show you some uh, it can affect you. For example, the phase bias will on the mixed pixels will cause some extra signal that is not deformation. So you may want to set minimal btemp to something higher. Say you start in 20 days, yeah, just to avoid all the influence of the vegetation there. Okay, that's fine tuning things. Just saying that you have the uh, options here. So you can just run the command. So finally I run something so you can see what it does. So it gets all the it gets the standard default values. It checks if the data are actually readable, and then does the stuff, and then informs you how many interferograms here. In this case, 30 were discarded from partner processing because the unwrapped coverage is very very low. The same goes for the coherence. And actually, you can see the outputs of the step. Each of the step has some output that okay, sorry, this in this case I have already pre-processed everything, so let's see only particle thing, but you can see the bad interferograms, for example, in the TS folder. Everything was started on 1.1 is a result of the step 1.1. So you have interferograms that were selected as bad ones in step 1.1. So you can see them. These are links, so this was fast to generate. You can again check the stats in the folder info. Everything what starts on 1.1 is related to step 1.1. So you can maybe think if there is any other threshold that you can use that would improve your input data. Basically, you can see that most of the data are fully unwrapped. Yeah, almost 100%. With coherence, average coherence is mostly 0.3, or that's great. So you can simply drop everything what's below 0.2, just to be on the safe side, because low coherence very often means unwrapping errors which we want to avoid. So we can see one of the discarded interferograms. So see, I'm checking the TS folder, 11 bat IFG, and I'm selecting one of those that I've seen here. Yeah. So let's have a look at one of them. And yeah, it looks like this. So of course, this is interferogram that you don't want to put into the processing, right? So it's good that it got discarded. Let's get further, and finally here we have the network plot that I wanted to show you before. So step 11 will generate the network plot, and in our case it looks like this. So this is our input data set, and the blue lines are all the interferograms that we had that entered the stage 1.1 or 11. You can see each epoch has at least 3 connections with subsequent data. We don't have really long interferograms here. Okay, well, we don't need them. And some of those interferograms were indeed identified in step 11 as wrong and were removed. So that's what this network plot shows you. Okay, so that was a basic check. Now a little better check with yeah. So a little better check is the step 1.2 analysis here, which is performing the loop closure test, which I explained in the presentation. So we have basically 3 interferograms, epoch 1 with epoch 2, epoch 2 with epoch 3, and epoch 1 with epoch 3. If we put them together like this, the difference that we call loop phase closure should be 0 everywhere. In this case, it's not. And you see that it's not by jumps. If this one is a big jump from 0 to some other large value, you can see that indeed it's probably about that the longest one. This is probably a rapid error because the other two went quite smoothly here. And this it seems like jump. Sorry for the color scale. It's yeah, it's yeah, we should improve that one, I think, because it's not that visible, but you can see the clip in the loop phase. So you can also see the small bits, and that's not really unwrapping errors. That's the phase bias then. So unwrapping error would always jump by yeah by 2 pi, yeah, like k times 2 pi, and where k is integer, and the residuals that are just some smaller number, that's due to the phase bias effect of the multi-looking that I try to explain somehow shortly, just to get the idea. So we can actually keep those tiny changes, like we can get some noise there a little bit, but that unwrapping errors is a big problem. So you in the first place, in this step, or in the original approach, let's say, what we do is we estimate the overall average RMS E based on that. So if everything was 0, RMS E would be 0. It's not so. In this case, it's 2.26 radians. Okay, for the whole scene. Now, I will best show you again by showing the help, I think. I'll scroll down here to the usage. So okay, so this is clear. This is where it will be stored minus e, and that the radians, that 2.26 per whole scene. That's the overall, or yeah, that's the RMS E that will be used to filter in this stage by minus L. So minus L is threshold of RMS of the loop phase. This is the default value, quite strict, and especially strict because it's an average for the whole scene. In most cases, the issues with the unwrapping errors will be on one side of the screen of your scene. Yeah, some tricky area that you can get rid of if you are clipping, but if you don't clip and you have the unwrapping error areas there, it will always increase your RMSE, and you might be losing data that would be otherwise valuable in your area. So it's good to know what you're doing, right? Like if you keep this strict default value, it might happen that most of your uh, scenes will be discarded. Yeah. So that's one thing. And second, that's that's the original version. That's the stable version. You know, in Linux you have stable releases that can be 3-4 years old of any library, and then you have these unstable or testing releases that actually have the modern day functionality. And this is similar. Like this is from the stable release that we can still use. Don't be strict here. Instead, what we do currently use with this unstable is we are letting we are simply removing the loop errors pixel wise rather than dropping the whole interferogram. So so and that's a little bit tricky. So I have to tell that um, it's good idea to increase the threshold of the RMS of the average to something higher, say 15 radians, yeah, let's say 10 times higher, just to really remove the interferograms that are totally bad. And then keep running the nullify, which would do the rest, do the pixel-wise nullification of the unwrapped data that are wrong based on the loop-based closure test. Yeah? So there is a example running the command. Oh, I can try to do it here. If I will put the no PNGs because that takes actually this is the longest time. Running is using the no PNG. Multi-prime, it's just yeah, it's only median fix before the running, so it's always good to add it, but it's not that big. And I will set the loop closer to 15 or okay, just 5 because we have a really small clip. So I'll run in this way with nullification. With nullification, it will run a little bit longer than without it. That's true. But see what will happen. I didn't try it here actually. It should work. So it informs you what it is doing, in which step, and yeah, that's it. And then afterwards, you can have a look on some information. The idea is that we are serial. We try to really pick up the errors, the bad things before we will proceed into the final inversion. So that's the more careful things. And there is, apart from what I said, there is actually nothing much to say about that, I would say. Um, yeah, but it might really take 7 minutes here. So yeah, okay, let's see. That's the notification that takes them longer times. Maybe I should skip it because I don't know. It will be 10 minutes. Um, well, I will stop it because I can. Things were anyway preferences there, so and the notification it will just improve things, but let's run it without that. That will be much faster. Okay. Oh, it already did. Yeah. So okay. So there are some extra information. So as I mentioned, we are working on the loops. So we are working with all the interferograms that form some triplet, right? but not all interferograms have the triplet, so we cannot check all of them. And so there is information that there is 64 interferograms without loop. So it basically says careful about that, because if they are wrong, it will negatively influence your result. But there is a way, for example, to avoid using them again by some optional parameter if you want to be really sure that you are not adding error there. Okay, so in the end, nothing got discarded. Yeah, because we have nice data set, and the whole network is connected, so there are no gaps per se, but there can be on pixel-wise gaps also. And here, when I've run that, I can see some basic information about overall RMSE, which is very low actually in this case. Sometimes it jumps over 2. Well, we could have a look on this particular triplet. How does it look to think if we want or not remove it? But after referring it to the median of the scene or to the reference point, I'm not 100% sure now. We are getting the RMS is very low, so that's before the referencing. So we are interested in the last one, and you can see that our data are very good with very small RMSE. So we would not drop anything. But we can see that this step 12, that's the previous processing where I had this 1.5 radian actually. Yeah, so it found something just for me to show you, and there is one example only. So yeah, here is just example that it has the loop phase that is quite high, but that figure is without it's before referring it to the one reference epoch. That's strange. That's first the column, the first column that will get anyway fixed to a small number. So that's not a problem. So I'm surprised honestly that we generated these PNGs in this stage. It should be important is that it's not used actually that PNG files, right? Because we are using the second value. Okay, something forgotten. Anyway, it doesn't affect the functionality. So we can check the loop. Yeah, the interferograms that do not form any loop. We can have a look at that, but we will not do it. And we can afterwards check the network, which looks exactly the same as the network 11. Here it is after step 12. It didn't drop anything in this case, so it looks the same as 11. But it's good to check actually the network PNG plots every time, because you will see if everything blue turns red, you don't want to continue. You want to change the parameter to actually pass some interferograms. But anyway, that's that's all about that part. The important is inversion, small baseline inversion, and here we actually transform that network into of interferograms into the time series, which is the key thing that we want to do, right? So we are still fine on time, and there are indeed a couple of parameters that you can set and play around, but it's not that many of them. Basically, what can be useful sometimes, instead of the original least squares algorithm, you can use the coherence to calculate the weights, and then use the weighted least square is slightly better inversion. Like if you have some pixels with low coherence, it will not affect the ones that were actually correct. So that's always good to use, I think.
So then you normalize by the coherence in the weight. So the weighting is very coherent.
It's we estimate variance based on coherence. Yeah. And that will be used as wait a minute, weight is wait a minute, so 1 over variance will be the weight that will be yeah used in the weighted least squares. And we say normalize, it's a little, I'm not sure if this is the best term, because you indeed you scale it and then you scale it back, so you are not like changing the values, right? It's just you want to add the weights. So yeah, I think there is nothing much to change here. Um, or mention you. Okay, like there's, for example, I mentioned before, you can use offsets. You have the cosmic offsets. If you have dates with the earthquake, you can put them here, and it will estimate the steps. So that's in this stage. Yeah, okay. I think that I should perhaps mention only about those two parameters, singular and only SB. Sounds a little bit strange, but sometimes you can get into the situation where the original LiCSBAS approach will take a long time. Let's say singular would do basically the same. Well, there are differences. But now I'm speaking about the performance. So here you would have your result faster. The estimation of the interpolated parameter is different. It's simpler, but sometimes it may be even more correct. Sometimes in non-linearity, for example. Only SB would perform only SB processing. That's the most reliable thing to do. Like no interpolation at all. So if you want to use only data that where you have them, you can just set it with only SB. It will also run very fast. Wait a minute. What did I do? No PLC. I can show instead of singular. I will use only SB, and we'll run the command, and it should be in very fast. Still some issue with the matplotlib layer, so hopefully it's not a big deal. There's some little explanation of that. There is also singular cows, but I not play with that one. It can get you into some unexpected signals. Let's say so. So yeah, just keep it this way. So there is another possibility that some of the epochs will get removed, considered really bad, but that's rare, let's say. Here you have your final network, basically. Looks good, and you have also some. I'll show you. After the step 13, there will be a lot of data in under a results directory, which would include PNG files, and we can have a look at one. So let's see the velocity, vel.png. Let's display that one. So this will be velocity after only SB. So here it is. So what happens? There are a lot of patches. If you remember before the interferogram, that was smooth. You would get the signal everywhere. Here we don't have signal everywhere. Okay, that's because in some unwrapped data had not had the nans in pixels, right? So we unwrap each interferogram, and some interferograms may be low coherent, so we mask it, not unwrap that area. So there are nans. Therefore, there is a gap in the network for each of the pixel, right? You don't see it in the network because the network is for all the interferograms, but pixels would vary with that. Anyway, we see some velocity. We see already the result. It's looking nice. We see indeed uplift that is as expected, also from the GNSS in millimeters per year. Just we don't have that much pixels. So that's the effect of the ONSB. And that's what you can get from things like stamps SB, for example. You will get SB. If there is a gap, it will not get processed. So let's see if I will do the singular, which I showed the difference here. Like if you run it with the standard approach without, it will take 25 minutes. With singular, you can expect 5 minutes, 7 minutes, or something like this. Indeed, there is a notion that the separate subset will be corrected in lower precision, but for our purposes, it's not enough. So I'll wait for it, and then we'll rerun that cell just to see updated velocity where all the pixels should be should have the value. So so that's about the inversion. In the meantime, because you can see clearly how it's running 800 vantage points. Okay. What can I tell you? Oh, there is. Maybe I should mention about the memory sizes and stuff. So key parameters for the processing related to performance. So you can set different number of processing cores. I don't think that you would win anything if you put very high, like over 48 processors. Well, if you have them, you can give it a try, but I'm not sure if it's that much needed. Mem size. See, I have set 1 gigabyte here. Okay, this is a small area, but now the idea where I wanted to get is these two parameters will actually lead the patching mechanism of LiCSBAS. So you can see that here, because we allowed small memory, we basically say how much of data we can load to the memory in overall. So in this case we have small area, so there is only one patch for that area. All our data are loaded into memory to be processed by one processor. But if you have more processors, it will probably create more patches, let's say 5, and we'll process them in parallel. I said 5, but then it depends on the memory size. Like if you have an normal memory, it can still try to run on one patch. There is also some parallelization, but it's better to actually decrease the memory a little bit, something reasonable, let's say, I don't know, 16 gigabytes, 8 gigabytes or something, just to see several patches, because the parallelization is actually benefiting from running on multiple patches. It will just run faster. So so this way it's also like saying like you can run it on small computer. You don't have extreme memory because the patches solve the situation. Plus, if there is really no way, then it will use the HDF5 file directly on disk that will be loaded like instead of memory. So it's well prepared. And okay, here we are. This was processed, and you can see the velocity. Now we have all the pixels because whenever there was any gap in between, it got just interpolated through it. So and there was linearity, we know about that. So this is appropriate assumption. Okay, so that's the velocity, but can we trust it? Well, we can calculate STD, or let's say standard deviation of the velocity, we can say it this way, by the bootstrapping. So that's also very nice functionality, and I'm also somehow frozen. Why I cannot? Okay. So there is nothing much to set. You just run it and that's it, basically. Yeah, well, yeah, that's so that will run fast and it will generate VSTD, like velocity standard deviation estimated by bootstrapping. And yeah, okay. here it is. So basically, you can see the values are all very small, but in this area that is of our most interest in, we still have values of the STD around 1 millimeter per year. That's probably fine. You would most probably you will see on time series some sort of like non-linearities that cause that value. It also generates something called STC, spatial temporal consistency, which is also a nice measure. Well, you can read about that in MDPI paper from LiCSBAS, for example. The idea is basically to get noise. You can see the noisy patches also here, but that's working on the local window variances, let's say, while VSTD is anyway affected by a reference area. And you can see that the spatial temporal consistency of that region is good. So that's important. And finally, you can plot all the noise measures that are generated with steps 12 and 13 in one go. So you can really see about your what quality of your data set. There is just one file, mask TSPNG, that will be generated after 1.5. 1.5 is indeed about masking. So you have created time series, you have values everywhere for all the pixels. You get some measures of the error, and you try to pick up which ones you don't want to trust, which ones you want to mask away. There is, for example, max time between gaps. So basically, it means those two are related, yeah, max TLN and gap. So n gap means number of gaps in the time series. So it means that those pixels have okay, I cannot tell you now because it's saturated, but maybe 10 gaps or something. And we can mask. Let's not trust anything that has more than 5 gaps. That's this case. And in relation to it, there is the maximum time between the gaps. So if we have 1 year between the gaps, we still can trust it. If there is so many gaps and basically every month there will be some interpolation, that's probably wrong, and we don't want to trust it. So that's the idea. And yeah, there is number of unwrapped data if you need this, but yeah, that's nothing much. Residual RMSE is very useful value because that actually tells you about the quality. Like basically, Resit RMS will tell you if there are unwrapping errors. So it says that in this area there is plenty of unwrapping errors, and those unwrapping errors went into the inversion. So you can mask based on this. If you use nullification, the Resit RMS drops down because you don't use that pixels that cause the error, but that can be misleading, right? Because what if you what if LiCSBAS mistakenly dropped the good ones and left the bad one? And that also can happen sometimes. So for these purposes, you should use some other other term. But the Resit RMS otherwise is very good layer to use for masking, together with everything else, coherence, average coherence, and so on. But the thing is, even when the coherence is low, even when the rest RMS is low or high, still the velocity looks reasonable, right? Here in this area. So in some cases you still can trust it. It's just more noisy. Yeah. Okay. So the idea is that again, if I will show the help here, almost finished. So here you have all the possible thresholds that you can use, the coherence threshold, STC threshold, and everything. So you can just run it once, see the result, and then you can change the parameter to rerun it, and then see again that PNG file that I just show you. So you can just fine tune it this way before the final step. What I wanted perhaps to mention is the relatively new average phase bias term in radians, and that can be very useful for that. I mentioned phase bias several times, so I don't want to repeat myself. But you can use it for masking, and once you will use it, it will show up in the mask TS file. So I can show, for example, um, 1 or 0.5 just to see a little bit more. Oh, yeah, okay. So here it shows you all the thresholds that were used and how many pixels or percentage of the scene was actually masked based on that um, particular thing. So and here is the final mask velocity where we indeed masked some areas and inside the TS folder you will have newly generated mask TSPH file that we can plot, and it looks like this. So this is the extra phase average that appears once you use it, not before. So it's good idea to just use and have a look afterwards and then fine tune it. And indeed, it shows similar area. So indeed, that place should not be trusted. It's probably okay. The average is also coherence is also very low. Don't know, maybe there's forest or something. But still, it's interesting to see that that areas look still fine in velocity. Okay, yeah, and everything else is saturated because we use too high values. You know, that's just basically if you want to skip masking based on VSTD, for example, you put high values, but then you don't actually see the VSTD. Sorry for that. Yeah, that's exaggerated. There is also another layer, n-loop error ratio. So this is basically ratio of errors, unwrapping errors that were found in the loops. So it means 7 will be like 70% of data has errors, which you don't want. Right? So you can again use it with minus big L threshold of error ratio. So if I will make it smaller, yeah, rerun it, and then okay, I use it probably much, but yeah, it's not too much. It's fine. And then it should change. Okay, well, you see there is actually no unwrapping error. Just a little bit here at these edges. So that's very nice data. So yeah, that's in the ratio. Okay, so that's it. You can mask, and once you're happy with your mask data, if this output looks reasonable to you, then you can finally do the filtering step, which does several things. Optionally, it can estimate and remove long wave RAM. Optionally, it can remove phase correlated to topography. Well, it's not really phase. This is after inversion that is correlated to topography, and it generates plots like this, so you can really check it. What you did is actually reasonable, because from experience, if you have, for example, only one mountain in your area and you would correct for AGT, it will probably scale everything around, so it will look like everything except of the mountain is actually moving like on waves of the ocean. So yeah, there are some specific things. So it's always good to check the generated pin. And basically, the safest side is just to perform spatial temporal filtering there, right? And I will show you out what else it can do, but that's basically it. Like you can remove the ramps correlated with heights and perform spatial temporal filter, which tries to capture the residual of the atmosphere. So it makes sense to just keep it by default as it is, but you can play around with the width of spatial filter and temporal filter. Yeah, and deramping if it's needed. There is an option to also estimate and remove TDM error phase if you think that you are using or that there can be some issue with DM error, then it would work, but we were not using it with the data before 2023. I think when the orbital tube changed actually afterwards in Sentinel-1. So before that, you don't have that estimate. Simply, you don't have that error there. So and just to show you that it's there, the options are all there. And after filtering, you're basically done, and you can run LiCSBAS.ts that I showed in presentation. That basically will show you the time series, and you can export it and use those several other functions that are briefly described in the tutorial. So you can have a look a little later. Now I hope I'm right on time. 1 minute off, sorry. But yeah, that's generally the idea. I guess that there is no really space for questions at this moment, but just I think I provided you the whole deep overview. So feel free to look into that a little later with Binder and rewatch the recording. For example, there are any questions, I showed you where to put issues into GitHub. I'm also here. People from our team are also here. If there are some particular questions, happy to answer, and you can always write to me. So thank you for now, and sorry that I finished just on time. Yeah, thank you. Stop it, bro.